Section 6.4, Trigonometric Identities. So remember that we have these things called identities, and we've learned a couple of them. And so let's think about this Pythagorean identity, sine squared of theta plus cosine squared of theta is equal to 1. And so what I want you to do is grab your calculator and confirm that these statements are true. That is, if I let theta equal 35, figure out what is sine squared of 35 degrees plus cosine squared of 35 degrees. Well, if you plug it into your calculator and your calculator is working, it's going to tell you the answer is 1. Well, if you let theta equal 5 pi thirds and then plug that into your calculator, make sure you're in degree versus radian mode for each one of these independently. And so sine squared of 5 pi thirds plus cosine squared of 5 pi thirds, check it out. What are you going to get? Once again, you're going to get 1. Now, the truth is that I don't care what theta you choose, as long as the theta you choose for both of these equations is equal. If you plug it into the Pythagorean identity, sine squared theta plus cosine squared theta, you will always get 1. Well, that brings up a good question. What makes an identity different from an equation? Well, an equation that is not an identity is called a conditional equation. And so, for example, let's say we had 2 times x minus 3 is equal to 5. The truth is, you could solve this via algebraic methods, and you would get that this is only true if x is equal to 11 halves. It's not true for all x values, it's only true for 1. Then, if I had sine of x is equal to 0, recognize that what we've now done via solving trig equations, we can figure out that the only time that sine of x is equal to 0 is going to be if we have an integer multiple of pi. And so, it's only true for those x values. And although that may be an infinite number of x values, it's not any x value. And so those two things are different. So make sure we're aware. Infinite is just a count. All means all. Alright, so let's go through the identities definition. And that is two functions, f and g, are said to be identically equal if f of x is equal to g of x for every value of x for which both functions are defined. Such an equation is referred to as an identity. And an equation that is not an identity is called a conditional equation. So everything that we just said a moment ago is still true. Now technically there is a little bit of concern, and that is for every x value for which both functions are defined. So technically if you have domain restrictions in one of the trig functions for which you're plugging something in, there's a little bit of working through that to figure out if it's still true. But I claim that as long as the domains exist, as long as the values in the domain exist for the defined function, then we're perfectly fine. Just to recall, what all identities do we have? So we have the quotient identities. Tangent of theta is equal to sine of theta divided by cosine of theta, and cotangent of theta is equal to cosine of theta divided by sine of theta. The reciprocal identities, cosecant of theta is equal to 1 divided by sine of theta, secant of theta is equal to 1 divided by cosine of theta, and cotangent of theta is equal to 1 divided by tangent of theta. The Pythagorean identities, sine squared of theta plus cosine squared of theta is equal to 1. But remember that really all you do have to do is remember this one, and if you can divide that all the way through by cosine squared of theta, you're going to get the second one. And then if you divide that first one again unchanged by sine squared of theta, you're actually going to get that bottom one, 1 plus cotangent squared of theta is equal to cosecant squared theta. And so my claim is you don't necessarily have to memorize all of them, but you do need to know them. Then of course we have our even-odd identities. Remember that cosine and secant are the only even identities. So, we're going to prove or establish identities. And so, essentially, the phrasing in this textbook says establishing, but proving or verifying an identity is the exact same statement. And so, there's going to be two primary methods that we're going to use. Method 1 is that when you have that function f of x is equal to g of x, the claim is you have to get from f to g. I'm thinking about f and g in terms of my definition previously. And so one method is you only change one side of the identity until it becomes the other side, and if you can show all the steps and define all the identities for which you used, you have done exactly that. You've proved the identity. Method 2 is that if you have two things being equal, you can start on the left-hand side, start on the right-hand side, and work your way to the middle until you find the missing link. And so both of these are viable options, but recognize that MyLabs is a little finicky on this, and so it's probably going to direct you in a lot of ways, so just pay attention. Now, some helpful hints to help prove these trigonometric identities. First off, start with either the left or the right side, and then try to get to the other side. And I would say work with the more complicated version. And so if you have two choices, pick the more complicated version and then work your way the other way. Carry out any algebraic manipulations such as adding, subtracting, multiplying, or factoring. Sometimes you have to multiply, sometimes you have to factor, so simplification or unsimplification may be necessary. Sometimes there's a trick of multiplying by 1 in disguise. Now remember, we can write 1 an infinite number of ways, such as 3 over 3, or sine of theta divided by sine of theta, or any other trig identity divided by any other trig identity, and so you might have to multiply by 1 in disguise. Also, there's a weird trick, and I'm saying this, you could add 0 in disguise, but if you add 0 in disguise, that really means you take something, subtract itself. Cosine theta minus cosine theta is 0, and so if you were to add cosine theta minus cosine theta, and then do some rearranging so that you can factor appropriately, that might be the trick that's necessary. Often enough, a good trick is to convert everything you see in terms of sine and cosine. Remember that all of our trig identities can be written in terms of sine and cosine, and so sometimes that's a good way to recognize how something will algebraically simplify. Lastly, in general, try something. So occasionally you just need to try some of these tricks that I'm going to show you and do things until you recognize something. I promise you that when I'm trying to solve identities, sometimes I fumble about. I don't always get immediately to my solution. And so sometimes you just have to try things until you get the connections that are necessary. Now, we are going to prove identities, but we're also going to need to be able to simplify trig functions as much as we can too. Now, I want to make a note, and that is simplification is not well defined. What that means is that when someone says simplify this trig function, there may or may not be a, quote, best, unquote, way. And so I'm just going to do these to where I think they're simplified, recognize that there may be another just as good simplification, and that's just a warning. So, tangent of theta divided by secant of theta. Well, part of me thinks I want to turn everything into sine and cosine. And so I'm going to use the quotient identity to rewrite tangent. And so tangent is really sine of theta divided by cosine of theta. And then I'm going to rewrite secant as cosine, and that's just 1 divided by cosine of theta. Then I see that I have fraction division. Fraction division is really fraction multiplication, sine of theta divided by cosine of theta, times the reciprocal cosine of theta divided by 1. But then cosine of theta divided by cosine of theta, that's 1. And then I'm just left with sine of theta divided by 1, or sine of theta. This one's simplified very nicely. Let's try this one. So we want to simplify 1 over 1 minus sine theta plus 1 over 1 plus sine of theta. My first thought is that I have fraction addition. And if I have fraction addition, maybe I can add the fractions. But to add the fractions, I've got to have a common denominator. And so I recognize that my LCD here is going to be 1 minus sine of theta times 1 plus sine of theta. And so I'm going to multiply both sides by a 1 in disguise. That's going to be, on the left-hand side, I'm missing 1 plus sine theta, so 1 plus sine theta divided by 1 plus sine theta. And on the right-hand side, 1 minus sine theta divided by 1 minus sine of theta. Well, then what do we get? On the left-hand side, I'm going to get 1 plus sine of theta times 1 all over. And sometimes it may be useful to leave it in the factored form. It may be useful to multiply it all together. I'm going to go ahead and multiply it together just in case something pops out nice. And so this is then, FOIL that binomial. That's going to be 1 times 1 is 1. Outer, minus sine of theta. Inner, plus sine of theta. Last, minus sine squared of theta. And then plus 1 minus sine theta divided by, notice that 1 plus sine theta times 1 minus sine theta is the same as we just found, so that's 1 minus sine, and actually recognize that minus sine theta plus sine theta, that's actually 0. And so this is really 1 minus sine squared of theta. I'm just simplifying it further. So then addition on top, that's going to be 1 plus sine theta plus 1 minus sine theta divided by 1 minus sine squared of theta. And so then on top I have 1 plus 1, that is 2. I have sine theta minus sine theta, that's going to be 0, so plus 0, I'm not even going to write that. And then in the denominator I still have 1 minus sine squared theta. But then the question becomes, can we simplify it further? And my claim is, yes we can. And the way that I can do that is I can use the Pythagorean identity. So I remember that cosine squared of theta plus sine squared of theta is equal to 1. And so if I solve for cosine squared of theta by subtracting sine squared of theta on both sides, I'm going to get that cosine squared of theta is equal to 1 minus sine squared of theta. Got to be careful, sine squared of theta. And then that is 2 divided by cosine squared of theta. And then at this point, maybe that's simplified enough, but I can get it to be a product as well, and so an equally good simplification is going to be, using the reciprocal identity, cosine squared in the denominator is the same thing as 2 times secant squared in the numerator. And so honestly, which one's a better simplification? That's going to depend entirely upon what the need is for this function. And so both of these are good equivalences. It's just a preference at this point. Alright, let's simplify this one. We have 1 minus cosine squared of v divided by sine of v plus cosine of v times sine of v. I can write 1 minus cosine squared of v as sine of v, as sine squared of v, so that's going to be via the Pythagorean identity. Cosine squared of theta plus sine squared of theta is equal to 1. I can subtract cosine squared of theta, subtract cosine squared of theta. Sine squared of theta is equal to 1 minus cosine squared of theta, which means that I can write the numerator now as sine squared of theta. This may or may not help. I could have to backtrack. Okay, so just be aware that sometimes you try things and it does work, sometimes you try things and it doesn't. I'm also going to look at the bottom, and I think that I can factor out a sine of v. And sorry, to make this match, I wrote it as theta. I need to keep that same variable that we have here, so I need that v here. So this is really sine squared of v. And so I see that in the denominator I have a greatest common factor of sine of v. And so sine of v factored out is going to leave me with 1 plus cosine of v. And so then because I have sine squared of v divided by sine of v, that's really one of those sines cancel. 1 sine divided by sine is 1. And so this is the same thing as sine of v divided by 1 plus cosine of v. And this is a perfectly good simplification. Now, I actually want to show you that there does exist another really good simplification that's very similar to this one that may or may not be better. And so I see that 1 minus cosine squared of v is actually a difference of squares. Remember that a squared minus b squared is the same thing as a plus b times a minus b. And so if I want, I could also try this idea where I can factor the numerator via difference of squares. That's going to be 1 plus cosine of v times 1 minus cosine of v. And in the denominator, well, I'm still going to factor that sine of v, but that's sine of v times 1 plus cosine of v. And so then I've got 1 plus cosine of v divided by 1 plus cosine of v. That's going to be 1. And that would be 1 minus cosine of v divided by sine of v. And recognize that via this, these two things are actually equal. Which one's better? That's all going to come down to preference. But I claim that these are both pretty good simplifications. Let's try another. Here I have sine of theta times cosine of theta divided by 1 minus sine of theta minus cosine theta times sine of theta minus cosine theta. Alright, so I'm just going to multiply this stuff in the denominator. This is two binomials, so double distributive property, or you can call that FOIL if you want. Sine of theta, cosine of theta on top stays the same. 1 minus, do be careful about a set of parentheses, because that minus applies to all of this product, and so we've got to watch out for that. Then sine of theta times sine of theta is going to be sine squared of theta. Then I get minus sine of theta cosine theta. Then I get minus sine of theta or cosine theta sine of theta, but to keep the order right, sine of theta cosine theta, because commutativity of multiplication, the order in which we multiply things doesn't matter. And then last terms, minus cosine theta times minus cosine theta is plus cosine squared theta. Okay, how did that help me? Well, at this point, recognize that I have sine squared theta plus cosine squared theta. And I remember that sine squared theta plus cosine squared theta is equal to 1. And so I'm going to replace sine squared of theta plus cosine squared of theta with 1. This is then going to give me sine of theta cosine theta divided by 1 minus sine theta plus cosine squared theta is 1 minus sine theta cosine theta minus sine theta cosine theta. Those are like terms, and so that's going to be minus 2 sine theta cosine theta. And then notice that that minus I can now distribute. That's then going to be sine of theta cosine theta divided by 1 minus 1 plus 2 sine theta cosine theta. Well, 1 minus 1 is 0, and so I get sine theta cosine theta divided by 2 sine theta cosine theta. But then sine of theta divided by sine of theta, that's 1. Cosine theta divided by cosine theta, that's 1. And so I get 1 times 1 divided by 2, which is really just going to be 1/2. So that's a pretty good simplification. Let's do it again. Here I have 6 cosine squared theta plus 8 cosine theta plus 2 divided by 2 cosine squared theta plus 4 cosine theta plus 2. I see that these are both quadratic forms, and so my thought is let's just factor these trinomials. I recognize that on the top 6 times 2 is 12, and two numbers that multiply together to give me 12 but sum to give me 8 are, luckily enough, 6 plus 2, and so I can use the AC method to rewrite this and force the factor by grouping. That's going to be 6 cosine squared theta plus 6 cosine theta plus 2 cosine theta plus 2. The denominator ends up working very similarly. I recognize that 2 times 2 is 4, and then 2 plus 2 is 4, which is the middle term, and so that's factoring as, be written as 2 cosine squared of theta plus 2 cosine theta plus 2 cosine theta plus 2. Now I'm doing a lot here. If it's easier for you to do just the numerator and then just the denominator separately, don't be afraid to do exactly that. Alright, but then I can force the factor by grouping. I'm going to do tops and bottoms. Top, that on the left I have a greatest common factor of 6 cosine theta times cosine theta plus 1. On the right binomial here, I have a greatest common factor of 2, so that's 2 cosine theta plus 1, all divided by the left binomial here has a greatest common factor of 2 cosine theta times cosine theta plus 1, and then the right one here has a greatest common factor of 2, so plus 2 cosine theta plus 1. And then I see that this factors as two nice binomials in the numerator and the denominator. That's going to be cosine theta plus 1 times 6 cosine theta plus 2, all divided by cosine of theta plus 1 times 2 cosine of theta plus 2. Then I recognize that I have cosine of theta plus 1 divided by cosine of theta plus 1. And so cosine of theta plus 1 divided by cosine of theta plus 1 is 1. So then I'm just left with 6 cosine theta plus 2 divided by 2 cosine theta plus 2. The question then becomes, can I simplify it further? And I claim yes, there's another greatest common factor I can factor out. So in the numerator, let's factor out 2. That's going to be 2 times 3 cosine theta plus 1. And in the numerator, that's going to be 2 times cosine theta plus 1. And then 2 divided by 2 is 1, and so I'm left with 3 cosine of theta plus 1 divided by cosine of theta plus 1. And I don't believe there is a better simplification than this. There may be, but I'm going to stop it right here. So now we're actually proving the identities. And so if I want to establish these following identities, I need to start on one side and get to the other. And so for this, I kind of look at them and I go, they look exactly similar. They look so similar to me that picking the left to start with or picking the right to start with, I don't see as being an advantage. And so I'm just going to start with the left-hand side. Sine of theta divided by 1 plus cosine of theta. And I want to find all of the steps to get there. Okay, I want to show that equivalence. And so if I can get the steps to show the equivalence, I have established this identity. And so let's see, what could we do? Well, I recognize that I need to get 1 minus cosine theta on the right divided by sine of theta. Now, part of me is saying, oh, well, I really need that 1 minus cosine of theta. And this is useful because I recognize that 1 plus cosine theta and 1 minus cosine theta are conjugate pairs. And so having conjugate pairs, or they're really the two pieces of the difference of squares formula. And so recognizing that, I think my trick here is to multiply by 1 in disguise. But of course, I've got to be slick about my choice of 1. So I'm going to choose that 1 minus cosine theta because I think something's going to happen in the denominator. And so multiply by 1 minus cosine theta divided by 1 minus cosine theta. So on the top, this is just going to be, I'm going to leave it alone, sine of theta times 1 minus cosine theta. If you happen to distribute it, you may have to backtrack. There's nothing wrong with distributing, but just recognize the equivalences that occur across the whole problem, because at some point one of the tricks might pop out. Well, in the denominator, I have a binomial times a binomial. That's going to be 1 minus cosine theta plus cosine theta. Negative cosine theta times cosine theta is minus cosine squared theta. That's then going to be sine of theta times 1 minus cosine of theta divided by, well, minus cosine theta plus cosine theta is 0, so I'm left with 1 minus cosine squared of theta. Then recall that we have the Pythagorean identity popping up again. Sine squared of theta plus cosine squared of theta is equal to 1. So if I subtract cosine squared of theta, I can get exactly what's written down there. That's going to be sine squared of theta is equal to 1 minus cosine squared of theta. So then I get, replace this with sine squared, that's then going to be sine of theta times 1 minus cosine of theta divided by sine squared of theta. But then I recognize that sine of theta divided by sine squared of theta, that's really one of them cancel with one of these, and then I'm left with 1 minus cosine of theta divided by sine of theta. And recognize that we have done exactly what we needed to do. We have shown that this is true. This is just a solid box. Sometimes if you end a proof, then you can say, oh, I'm finished. This is just to let the reader know that you've finished it. Something else that you may see in the literature is QED. It's just a Latin phrase for thus it has been shown. Alright, so let's establish this identity. Sine of theta times cotangent of theta plus tangent of theta is equal to secant of theta. Personally, I think the left side's more complicated, so I'm going to start with the left-hand side. And when I write this, I'm going to go ahead and write everything in terms of sine and cosine, because maybe that will help me get to secant theta. So, sine of theta times cotangent of theta is really cosine of theta divided by sine of theta. And then tangent of theta is really sine of theta divided by cosine of theta. At this point, how about we just distribute that sine of theta? Well, then that's going to be sine of theta cosine of theta divided by sine of theta plus sine squared theta over cosine theta. I think I'm going to go ahead and simplify it with that sine of theta divided by sine of theta is 1, and I'm going to get that cosine of theta plus sine squared of theta over cosine of theta is true. Now, at this point, it could be useful. You remember how we said we can look on the left-hand side, look on the right-hand side, and connect everything in between? It's probably useful to remind ourselves that secant of theta is really the exact same thing as 1 divided by cosine of theta. Because if I can get to 1 divided by cosine of theta, then we're finished, right? Because 1 divided by cosine of theta is secant of theta. And so I just need to figure out how to do that. Well, I recognize that I've got sine squared of theta divided by cosine of theta, and so maybe there's some trick about adding the fractions here. I know this doesn't look like a fraction, but it's a fraction. Figuring out how to add those fractions, and maybe that will fix my problem. And so I think that over here I want to multiply by 1 in disguise, get a common denominator. So my common denominator is cosine of theta, so multiply by cosine of theta divided by cosine of theta. This is then going to be cosine squared of theta divided by cosine of theta plus sine squared of theta divided by cosine of theta. Then this gives me cosine squared of theta plus sine squared of theta, all divided by that denominator cosine of theta. But then remember, I've got that Pythagorean identity, cosine squared of theta plus sine squared of theta is equal to 1, and so I get 1 divided by cosine of theta. Look at there, we're finished. We got secant of theta. And so we're done. Let's try it again. I have cosecant of theta minus cotangent of theta is equal to sine theta divided by 1 plus cosine of theta. Now, at this point, which one's more complicated is really a matter of preference, but in general, I believe that having the addition or the subtraction is the more complicated one versus the sine of theta divided by 1 plus cosine of theta. And so my preference is going to be start with cosecant of theta minus cotangent of theta and write it in terms of sine and cosine. And so cosecant of theta, that's going to be 1 divided by sine of theta, minus cotangent of theta, that's going to be cosine of theta divided by sine of theta. And so then, look at here, notice that I have common denominators already. So this is really going to be 1 minus cosine of theta divided by common denominator sine of theta. And if you recall, this is actually similar to that one we did earlier, if not exactly the same. Multiply top and bottom by that conjugate, 1 plus cosine theta over 1 plus cosine theta. Then let's see where we get. This is going to be 1 minus cosine theta plus cosine theta minus cosine squared of theta, all divided by, and I'm not going to multiply it out because I think I see what's happening, sine of theta times 1 plus cosine of theta. Then in the top, let's simplify that. That's going to be 1 minus cosine theta plus cosine theta is 0, so that's 1 minus cosine squared of theta, divided by sine of theta times 1 plus cosine of theta. And then I recognize that 1 minus cosine squared of theta is equal to sine squared of theta from my Pythagorean identity, and so that's going to be sine squared of theta divided by sine of theta times 1 plus cosine of theta. And then sine squared of theta divided by sine of theta is going to leave me with sine of theta in the numerator divided by 1 plus cosine of theta. And look, that's exactly what we needed, and so we're done. Here I have sine squared of theta minus tangent of theta divided by cosine squared of theta minus cotangent of theta is equal to tangent squared of theta. And I definitely think that the left side is more complicated. So I'm going to start with that side. And I'm going to play that same game of write everything in terms of sine and cosine and see what I can do. Also a side note, and if I haven't mentioned it enough, the proving of the identities is not one approach is always right. And so the truth is I'm doing what I see as fastest and best. You may see something better. You may see something that's completely different, but you arrive at the exact same conclusion. And the beauty is that if you learn the identities and you're proving identities, our approaches do not have to be the same, but we should arrive at the same conclusion using identities. Alright, so I'm going to rewrite this in terms of sine and cosine. So sine squared of theta minus tangent of theta is really sine of theta divided by cosine of theta, all divided by, that's cosine squared of theta minus cosine of theta divided by sine of theta. Alright, so what do I see jumping out at me? Well, I think maybe if I factor, it'll be helpful. And this may or may not. Once again, we may make wrong choices as we do this, and don't feel discouraged if you make a bad choice and have to backtrack. It's not a bad choice if you tried something. It was just not the best choice. So I think I'm going to factor because I see that the numerator is sine theta and the sine squared theta, and down here I have cosine squared theta minus cosine theta divided by sine theta. And so I'm going to factor out a GCF of sine theta times sine theta minus 1 divided by cosine of theta, all divided by cosine of theta times cosine of theta minus 1 divided by sine of theta. Alright, I kind of like where we're heading. And the reason I kind of like this is because if I rewrite this, that's just products, and so that's sine of theta divided by cosine of theta times sine of theta minus 1 cosine of theta over cosine of theta minus 1 divided by sine of theta. Now, why am I interested in what I just wrote? I recognize that my goal is tangent squared of theta. And I also recall that tangent of theta is the same thing as sine of theta divided by cosine of theta. And I see here that I actually have a tangent. And so I think that the fact that that's tangent theta, if I can find another tangent of theta by doing some simplification here or using some identity, then we're finished, because tangent of theta times tangent of theta is tangent squared of theta. And so that's kind of what I think I should do. That's exactly what I'm going to do. I am going to work on this top and this bottom and see what I can do to simplify it. Now, I'll tell you what I'm thinking. What I'm thinking is I have these complicated fractions in numerator and denominator. I think that what I want is some form of fraction division that then becomes fraction multiplication. There's a few more steps before we get there, but I think that's the right approach. And so, let's think about this for a moment. Alright, well, how can I do that? Well, really, I think I want to add these fractions on top and add these fractions on bottom. And so I recognize that these are fractions. And so here, to get a common denominator, I just have to multiply by 1 in disguise, where that 1 is cosine of theta over cosine of theta. And then down here, I want to multiply that by my 1 in disguise being sine of theta divided by sine of theta. Now I'm going to make a slight jump, but recognize that all I'm doing is cosine theta times sine of theta, and then cosine of theta is my new common denominator. And so what is this going to give me? This is going to give me tangent of theta times sine theta cosine theta minus 1, all divided by the common denominator of cosine of theta. All of that's divided by sine of theta cosine of theta minus 1 divided by sine of theta, which was that common denominator. Alright, I like this. Now I have a fraction divided by a fraction, which is fraction multiplication, so that's then going to be tangent of theta times, copy dot flip, sine of theta cosine of theta minus 1 over cosine of theta times sine of theta, all divided by sine of theta cosine of theta minus 1. I notice then that sine of theta minus 1 divided by sine theta cosine theta minus 1 divided by sine theta cosine theta minus 1, those two things are exactly the same. Anything divided by itself is 1, and so then I'm left with tangent of theta times sine of theta divided by cosine of theta. Oh, look at there. Then I get tangent of theta times tangent of theta by using the quotient identity, and then that's going to give me tangent squared of theta. That's exactly what we needed. We have now arrived at our conclusion, and we are done.